Let's start again. Thank you to all of you who stayed here instead of going to the other room. It's Johan Tibel. That was a tough contest, but tough competition, but okay. So the question now is, so far what I showed you may impress the Haskell crowd, but it's not going to impress the game community, the game programming community. And the question is, how are we going to take over, right? And I think it's just not going to happen. I mean, maybe if we tone it down a bit, yes, we can maybe afford, but not even that. Maybe we can just be there, you know, just show up, or at least not die. And so I think this is where the power comes in. It's in abstraction. This is how I measure the success of my programs. It's revenue divided, monthly revenue, or per time period, divided by the number of lines of code. I'm not impressed when someone says, I wrote this program and it's 1 million lines of code. I'm really not impressed. I'm impressed when it solves a problem. And I've had people telling me that this program is not good enough because it only has 2,000 lines of code. And I was like, you don't know what you're talking about. It solves the problem in only 2,000 lines of code. It's amazing. But some people really don't understand it. Every line of code is something that you have to maintain. So the shorter, the better. And so with good abstractions is, I think, where the power of Haskell is actually shown. One abstraction that I use a lot is functional reactive programming, which probably you have heard about. And the idea is that in all of these programs, you have a value, an entity that changes over time. Right? And that's just the idea behind reactive programming, not functional reactive programming. Functional reactive programming adds the time to the actual equations. So what you have is that you have signals. I don't know if you can all see it here, because it just went there. You have signals, which are values that depend on the time. And what you do is you're moving one level of abstraction up. And instead of describing how things change, instead of describing things operationally, you're stating things for all time in the same way that when you describe a function in terms of other functions, you're not saying, if I get this input, I modify it in this way. You're saying, this function is the composition of blah and blah and blah. That's the function for all possible values. It's the same difference. And the idea is that you represent the values in your program as values that change over time. Okay? So, for instance, a mouse position would be a value that changes over time. And if you want to have a ball following the mouse, what you have is that the picture of the ball at a particular time is the translation of a circle, or the movement of a circle, to the mouse position at that time. That's how you express it. If you want a ball to go around in circles, you say that, well, just take this picture. This is an abstract thing. I mean, it doesn't come from any library right now. Take this circle and translate it to this position, where the position is some radius times the cosine of the time. And that's the picture for all time. The good thing about this approach is, this one. You're not talking about sampling. So if the sampling rate gets increased, your system keeps working. It becomes just more and more precise. So you're talking about meaning, not operation. And I have an example here that shows what this means. The idea essentially is that you take time, let's see, that you abstract over things that change over time. And one way that you can do that is, for instance, you can talk about integrals and as something that adds something that changes over time, multiplied by the actual, so you can only approximate it. But if you want to approximate an integral, you don't need to know what you're integrating. You only need to know how to multiply it by the time that has passed, and then you can approximate it. And you can write these combinators like integral, regardless of how you're going to use them, and have them in a library. And then you can write functional reactive equations like this, which look just like the physics equations. And this is what actually goes in the program. So it's just add the initial position or velocity to the integral of the acceleration. and that's it, and that runs. So to show you one example of how FRP gets realized, which is, I think, also in the repository, and if it isn't, I'll upload it. Yeah. So this is collisions implemented in Yampa. And it's a very simple physics system with just circles. I mentioned that circles was the easiest way to simulate these things. What you see is that for each one of these balls, well, they're supposed to be round, but there's a problem with the projection system, so they're a bit stretched. But what you see is that this line shows you the direction where it's going, and this shows you the position where it is. And yeah. Oh, sorry, that's because I used a code from another. So this is funny. We were at Zurich Hack, and we started coding something with people we had never met, and we couldn't agree on the name of the program. And so a Googler said, you shouldn't argue so much about the name because that's how projects get killed. I mean, if you spend too much time arguing about those things, the project will die. So we called it Voldemort because it's he who must not be named. So what you see here is that in Yampa, in this reactive library, what you have is that you separate time completely. And you just express equations for all time. And then you add like the time when you sample. That's how it gets calculated. And let me see. If I run this slower, if I just slow time down, the simulation, like the rendering, is happening at the same speed, like maybe 800 frames per second. It's just being simulated a lot more precisely, right? So what you're seeing is that thing that we saw in the diagram, when a function just gets more and more approximated to the actual ideal representation. And I can even run it a lot, oh, that's faster, a lot slower, and get it moved pixel by pixel almost. Right? And this is completely abstracted away. This comes from this code that just determines how much time has passed. And the rest of the equations look like what I showed you with the physics and the integrals and all of that. So I use this implementation, this reactive library, a lot. And there's a reason for that. If we go back to this, okay, let's look at this example. Here we depend on, oh, not this example, this one, right? So here, yeah. Sorry? How it's possible to? Can you give a value of type? So if I don't, I should, and it's there written somewhere, but if I don't, remind me later because I should talk about that later. So here there's a few problems with this. One of them is that we depend on the mouse position, which comes from the external world, but there's nothing in the signature. This is a signal that gives us a picture. The type of this would be signal picture. When we do I/O, Haskellers like to have I/O there in the signature, and if it's not there, there should be some unsafe perform I/O somewhere. It should be clear that there's some access to the external world. But here, we access the mouse position, which is I/O, but this doesn't have I/O in the signature. So one problem with having all these external signals plugged directly into others is that it hides dependencies on the outside. And that's perfectly fine, because there's still, you can have implementations of FRP in which the mouse position at any time is the same for all signals. So in that sense, it's referentially transparent. At any particular time, it's the same value. And that's important. I mean, if you have a device that doesn't, for which if you get twice, you don't get the same result, having this referential transparency at any time is important, because otherwise you might get incoherent results. But I like to separate this and have signals depend on this explicitly, so that my signals are pure, absolutely pure, and then I just plug the external systems. And this gives you a different kind of referential transparency, which is from one execution to the next. If you sample at the same times and provide the same inputs, you will get exactly the same result. That's important because it doesn't happen by default if you don't do it. And one example, which I think I have here, are these simulations of FRP physics with, these are force-directed graph layouts. You have a few nodes connected by, I don't know, whatever, and if they're connected, oh, you took the bar, okay. If they're connected, then they attract each other. If they're not, they repel each other. It should stabilize at some point. And if everything being perfect, it should always stabilize to the same thing. This is functional programming, referentially transparent, but it doesn't because the sampling times are different. And just those tiny little differences are enough for things to accumulate and eventually converge to something else. And what you see is that I run the same thing twice, same graph from the same initial positions twice, and it converges to different things. This is a 2D thing that looks like two cubes, one on top of another, but it's just a 2D graph that stabilizes to that. But I run it again, and then it just stays there into that blob thingy that you saw, into this. It becomes that. And that's a stable equilibrium for the graph as well. And that only depends on the sampling times, nothing else. So that's more important than it seems, and the people who are doing now Elm, for instance, are having trouble going back in time, saving times, and making sure that they can replicate previous conditions and previous situations. And in Yampa, you can abstract that away. So one cool thing is that we can send, and this is something I want to integrate in my next game, we can send a game to someone, and when something goes wrong, we only need to know the sampling times and the inputs to be able to run whatever and see whatever they saw on our machines and be able to replicate the same deterministic state as long as the algorithmic unit does the same calculations, which we hope for. But other than that, as long as we get the sampling times, we can run the same thing. And if you see a bug on a game and you know that the bug happened at 3 seconds, you can just record all the inputs and the sampling times and then just replay back to 3 seconds before and see what happened. And if you slow time down, you can examine the situation a lot slower and see what's going on. And I have a draft paper on this, which I never sent anywhere, but it's there. We're also plugging quick check to this. And we have temporal logic in Yampa, so we can express properties of these programs using quick check, and we can get quick check to tell us what's wrong. So the cool thing is that you can start recording a game, and at some point you tell quick check, now you take over. And now you tell me if any temporal weird thing is going on or any assertion is being violated. And quick check will tell you. And the cool thing is that, for instance, for a game like Haskell, which is Haskell Breakout. This game, I'll run it in a minute, but you get the picture, right? It was able to tell me that the ball could go through a wall. And the way that QuickCheck did it generated a stream of sampling times and inputs. It just gave me as a result, okay, if you sample at these times and do this with the mouse, the ball will go through the wall. And I expressed that property in temporal logic, and what it did is it said, okay, initially you don't do anything, and then you move. The next sample should be with the paddle moving to the right real quickly, and the third sample should be in like 15 seconds. And because of the way that you're doing physics, when you sample at that time, you're not correcting the collisions, and at that time, the ball will be through the wall. Whether you correct properly or not, that's a different problem, but the ball will be stuck in a wall, at least for a frame. So you get, with this way of doing pure FRP, you get those benefits that come from the functional land in that sense. Let me see, where are we? Yeah. Okay. So a few things that we have done in FRP, for instance. No. Tutorials, FRP, I think. Yeah, so for instance, a circling ball. This is how you do it in Yampa, right? So Yampa, with these signal functions in which you have to explicitly name the signals that you depend on if they come from the outside world, what you have to do is you have to separate your game in 3 parts, which are very similar to the game loop that we talked about before. You sense, you process, and then you render. And in Yampa, it's called sensing, signal function is the processing, and activating, or actuation is the rendering, sorry. And the way you do it is there's a function called reactimate that, oh, I shouldn't have done that. It works is that every simulation has 3 parts, 3 arguments. This is the part that senses, and it senses 2 things. The input samples, which could be using SDL, you could pull the mouse position or whatever, and also the time, how much time has passed. And it gives you a delta time. This is the part that says what to do with the output, and in this case it's just displaying. And this is the part that does the actual processing. And this in circles is defined the way we saw, that you get the time and then you turn that time into coordinates. Here we're going to have a ball going in circles in the middle of the screen, so we have a center. And to that we add the cosine of the time multiplied by the radius, so that it just goes around depending on the time. Another way to write that in Yampa would be with the hateful arrows, which you just get the time and then you just calculate and return the coordinates. This actually looks more readable in this particular case. The rest of the program is standard SDL, like the one we saw. We just get the position, get the video surface, clear the screen, paint the circle, and flip it. And flip it, it just takes whatever we drew, and sends it to the graphics card all at once. It doesn't always work like this, but yeah. And sensing, in this particular case, there's no sensing. But if we have something like, for instance, something that should follow, a ball that should follow the mouse position, so it should just be where the mouse is. You sense, and then you provide that as a result, as part of the result of the sensing action. And that, let me see if I get a better example. Yeah, this one is better. So here we get the mouse position and we pass it as part of the sensing action, and in circles gets the mouse position as an argument. And it's going to circle the ball around the mouse. Right? But here, there's no explicit mention of the mouse. There's nothing that mentions. So you could take this and put it somewhere else, and it would still produce an in circles calculation. So if you want to put something else in circles about some other thing, it doesn't really have mouse position inserted in the function implementation. So it's more modular in that sense. Well, I only have that one compiled, which is the one this is just an animation of what we saw before, the integral thing followed. But let me see where we're. Yeah, okay. So FRP is only one of the things we're using, and I don't advocate that you should use FRP all the time or for the whole application. There's a lot of other things that we also use. I use reactive values a lot, which is an abstraction over things that can change, but for some user interfaces, like if you use GTK, they're not going to, using time doesn't really make sense. Adding time there doesn't really make sense. You don't have animations, you have discrete changes. So in those cases, I just have like a reactive thing that will notify me when there's like a change. And then I connect them somehow in the program. There's also something that we saw is that sometimes the same thing that renders the output can also give you input. For instance, if you have a widget system, you render the widgets, or you refresh the widgets, or you refresh the properties, and the same widgets will also give you input to your system. There's an abstraction for this called game views, in which you have kind of like an endpoint, which could be a player. The player is the ultimate bidirectional input-output, right? But it could also be AI. An AI system could be just something that reads from your game and writes to your game. So there's a lot of abstractions that we're trying to find out in this sense. Many of the solutions come just from imperative programming, game programming. But we're also using reactive values for this. So the idea is that you have something that you can write to and read from, and you connect it to your functional reactive thing, and whenever it changes, it updates, and it also produces changes that the signal function consumes. We're modifying Yampa to know what parts of things have changed. And at some point, someone asked about, I think it was you who mentioned the game loop, that it could be desynchronized. Or, yeah. So to answer your question, when you do something like that, imagine, for instance, that you're simulating your physics. And you need to know, to play a sound, you need to know when a ball hits the wall, because then you should play a sound. You simulate physics once, and then you tag in your model. You say, well, now I hit the wall. But you don't render that time. You don't play sound that time, because the end point, the rendering system is too slow. So you simulate the physics again, and you don't know that it wasn't rendered. So normally you would just disable that thing and say, well, now it already, that's already in the past. And what happens is that the rendering system would miss that event. So usually when you decouple things using different threads, you no longer can just pass the state. You have to pass events. You have to add a sense of events. And the way we're doing this is with channels. So to communicate this state, you have an envar or some sort of like a holder for something. Events are just channeled and accumulated. And sometimes what you have is that some events destroy the whole queue. So for instance, if you're in a menu and you start playing and you press the enter key many times at the end of the menu, when the game starts, it shouldn't process those keys that were in the past. So what you have is the game state goes in an envar. Whatever changed in the state goes in a queue of events. And some events can just erase the queue. Oh, this is interesting. So in FRP, one thing that we're using is creating subgames. And the way it works is like, let me see. Yeah. So this is a breakout game with menus. And what we're doing is we're organizing the game in subgames, each of which has its own input system, processing thing, its own renderer, and well, it's a rendering action. It's not really a renderer. It's just a rendering action that will get executed on the main renderer, and its own logic. And that means complete games become compositional. So here in this breakout game, we have two parts. One of them is the menus, and the other is just the action, so to speak. And the game state of the action part doesn't know anything about menus, preferences, level selection, or anything like that. It just knows the status of the game, where it's playing or paused, the lives that you have left, levels that you have left. But it doesn't know anything about any other part, so you could integrate it into another game. The output, for instance, is also done this way. So it takes a game state, running game state. It doesn't take an application state that could be one or the other. It's specific for this particular state of the application. And then there's a state machine written in FRP, that would be here, that just makes sure that the application transitions from one to the other, from one logic to the other. So in this case, initially, there's a menu sub-application, And when that ends, it tells us the preferences of the game, difficulty, sound, volume, whatever, and where it should go. And if it should go to the game, then you run this other sub-application. These are signal functions. These are functions that take a time-varying controller and turn it into an application state. And yeah. If you've ever used Yampa, you probably hate switches too. Switches are something that comes with Yampa that allows you to start transforming something in one way and then start transforming it in another way. And then you can modularize your program by saying, this is the first way to transform it, this is the second way, and then I can switch from one to the other. But switchers are really confusing. So what I use is, I use this syntax with slightly, this is something I introduced. It's probably going to make it into the next version of Yampa, or at least I will put it online. The idea is that this produces two things. One of them is its output all the time, an output signal, and another is an event, something that may or may not happen. And when it produces that event, it tells you also, it can give you a value inside the event. It can give you something useful for the future. So in this case, it's producing, the main sub app is producing, oh, no, this one is the event. Must quit is the one that detects the event. So the way that switching works is that you need to have a main signal that produces the output and something that tells you when you have to behave in a different way. And here, you're just putting these two together and saying, this is the main behavior until this happens. And this will be detected, and then it will start behaving like that one. Until S has the same type as switch in Yampa, which has this type. Yeah, that helps. It takes a signal that produces an output and an event, and as a second argument, it takes whatever came in the event and the new way of behaving or transforming the input signal into something. Yeah, does that make sense?
Yeah, so an actual signal function sort of ends when you can say how it should change.
Yeah. There's something in Yampa called task, which is supposed to abstract over this, but I don't use it. But the idea is more or less the same. So it could end. What's important about that is that, so Yampa, one of the things that it does is that it keeps state for you. So integral, for instance, remembers what it simulated already, and when time passes, it just calculates the new value, multiplies by the delta, and adds it to what it already had. If you, let's say that you switch into a signal function, you have a signal function, you apply it, and at some point you switch into itself. That integral is going to be resetted, because this is like having the best diagram for this is the one that you have, like signal processing thing. This is like having one component, and suddenly I take it out and I put another one in. Now think about it. If you have an actual board, and you remove one component and you take another, and you plug another during runtime, the new component doesn't know anything about the state of the old component. So you're inserting it for the new component. That's time 0 when you insert it. Same thing for Yampa. So you have a sense of local time. If you switch into something in the middle of an execution, then that's time 0 for that thing. And if you want to remember all things, you have to pass them explicitly. Sorry? Yeah, that's what comes in the event. So the T is what comes in the event. Here, the first signal function will give you the output and whether it's time to switch or not. And if it's time, this is isomorphic to maybe. Event is isomorphic to maybe. It can be no event or just an event carrying one value. And it's all the information that you need to know to go on. And this is used in the continuation to produce a new signal function. right? So it depends on when you don't. So you have to do it explicitly. There's no specific support in Yampa to move forward in time, move a signal forward in time or backwards. There's a there's a fork of Yampa that it's on GitHub. It's on the official repository. I use branches all the time for this. And there's one that includes time transformation mechanisms. But we have to be careful with that. And the reason is that time in FRP always has to go towards the future. Because otherwise you get weird, strange behaviors. Like, for instance, you poll the past and it doesn't behave like it used to. Or even worse, if you give the ability to poll the past, then you have to keep it forever. And that's a huge problem, like a huge leak in most FRP implementations. Well, all the FRP implementations. The new ones all try to work around this problem in some way, either by not Yampa. What it does, it just doesn't let you go into the past. So there's the now, period. Yeah, that's essentially what would happen. If you let people go in the past, that's essentially what would happen. There's an FRP implementation called Unity by the University of Twente that doesn't take this into account, and it could create grandfather paradoxes. Okay. So where are we? To give you a sense of how big these things are, I think this game is something like 1,000 lines of code. Okay. The game that you saw before, the one that wasn't that impressive, but you could actually might be able to get your nephew to play. This is 276 lines of code with spaces and comments and imports, which I never count the imports. And with Wiimote support. Isn't that amazing? I wrote like a very simple board game. It's on my website in less than, I think it was 80 lines of Haskell or something. Yeah, so that's, I mentioned this before, and wait, where was it? Yeah, that's actually important. And using the right abstractions, one of the things that I see is that I can open a program that I wrote like 3 years ago for a client. They request a change. And because I use the right abstractions, or good abstractions, I didn't invent them, but I use them. And I know where the change should be. And because it's Haskell, when I break it, because I'll break it, because it's been 3 years, the type system, the type checker will complain. So, but this is really important. What else? What else? What else? So yeah.
With the menu sub-game.
Yeah.
So you have 2 times. One is the time for the ball and for the bricks. The time with
that. The menu in this game is a menu like you first go into a menu and then go into a game.
Okay, but hypothetically, the other time could.
The question is, with what I've showed you so far, what can you do, right? There's a lot of information already that you can see on this website. I also put things regularly on our Facebook page, but you can get assets. For instance, these assets, I didn't create them. There's assets online that you can use for a game. You already know how to use basic SDL. There's also a tutorial on SDL there. There's tutorials on Wiimote. And there's going to be there's code, and there's going to be a tutorial on Kinect, and a lot of tutorials on SDL2 as well. So you have already everything you need. I mean, you have the assets for free. You have the skills. So now the only thing, yeah.
There was another bit on the other slide with the 3D.
Commands that the graphics card can execute. So it renders directly. It executes directly on the GPU, and they created this, which unfortunately I don't think I can zoom in because it just gets displaced. Yeah. But this is a rendering engine written in Haskell. And I think this is a Quake 3 scenario or something. And I think it looks pretty cool. So definitely, this is not Haskell is not a toy language for game programming. Absolutely not. The problem with this kind of approach, in my view, is that you're never going to convince people who are going to use Unity to create a professional game that with $1 million budget to use Haskell. It's really hard to convince them. It's a circle, right? Yeah.
But you might not convince them,
but then you can't afford the assets. You can't afford the artwork. That's the problem. You probably cannot afford all the things you need to create a game that requires this kind of rendering. Wait, don't take the picture now. I'm showing somebody else's work. Wait. Let me see. Cool. No. Yes, I did. Right. So, yeah. As a community, the question now is, where are we really? I think Haskell is in a unique position. We have a Windows, Mac, and Linux backends. It compiles to the browser, to JavaScript, so you can run Haskell on a browser. There's an officially supported iOS backend, so that you can write iPhone applications in Haskell. I don't know the state of that. Last time I asked, it wasn't so good. And there's an Android backend that is not officially supported, but actually works reasonably well. We could, in a few years, we could have one of the very few languages that just compiles everywhere and runs everywhere. And it's functional, and you can write games or programs in just a few lines of code. And for instance, in Yesod, I also create websites, and I have a client, and they needed a website. It was for task management and opening issues and reporting problems with other things. And I created this in Haskell and Yesod without knowing Yesod in like 24 hours. And it has like a proper email notification system that sends me an email when they open a new issue, and I can close them and open and assign time to different issues so that at the end of the month I can send them an invoice and they can see the invoice there. And it took about 24 hours of Haskell. And the cool thing is that because of the type system, if I break something now, it will tell me. So if I, like 3-6 months later, I open the application and I break something, I will still know. So I think Haskell is in a unique position in this sense. And this is a monkey coding problem. It's not really like we need amazing brains to solve. We just need to code. We just need to support the backends. We need to put in the time and actually do it. And then we will be in a perfect position to sell Haskell as a mainstream language. And for games, we actually have everything we need. There's nothing, if you ever consider writing a game in Haskell, if it's like an indie kind of thing, like arcade, 2D, you can do 3D, but if it's 2D, it's absolutely, there's no question that the only thing standing between you and releasing that game is you. There's nothing else. And we have done a lot of work already using Haskell. I created a game engine, which is this one, in less than, I think it's 2,300 lines of code. From this, by the way, I wrote like 4 years ago. So today it would probably be less, but it can run basic graphic adventures in Haskell. And this runs on Android, it runs on Windows, it runs on Linux, it runs everywhere. There's a whole development environment for it. That's not included in the 3,000 lines, but there's a whole development environment written in Haskell as well using GTK. That's something like 20,000 lines of code. And it uses the reactive value abstraction that I mentioned. And the idea is that designers can put together these kind of games by just loading sprites and creating actions, but they don't have to do it to know anything about programming. There's a few games that you can see online. This Haskell thing is not so impressive per se, but it also runs on Android. This was the first game that we got running on Android. And it uses the, let me see if you can see it here. Oh, well, I think you can probably see it here. So it uses the accelerometers to move the thing, to move the paddle. This is something that SDL gives you. You don't have to do anything special for it. Sorry? Operating system? This is Android. Yeah, yeah. Yeah, so that's what I was talking about. Yeah, you've been off for like 10 minutes. No, I'm kidding. It's a joke, it's a joke. So we have, there's an Android backend for GEC that is not officially supported, but it actually works. And earlier this year, we released, let me see if it's here, the first commercial Android game written in Haskell ever, which is really simple. It's a board game. The code right now stands at something like 1,000. It used to be 2,000, but I think right now it's only 1,000 lines of code. And it does all the proper things that Android applications do, like it behaves properly, more or less. It doesn't run forever, or it doesn't destroy, I don't know. It doesn't turn black when you abandon the activity. It has to manage the activity lifetime. It has to remember when you close it where you were, because Android applications can close anytime. So essentially, if you get a phone call where you're playing, your application gets killed. It doesn't run in the background. It just gets killed. So you need to save your state. And that means we need to talk to Java a lot. And a lot of the work comes from talking to Java and getting Java to save the state of the program so that we can recover it later. And it's a very simple board game, but the idea was to make sure that Haskell run everywhere first, and then we might be able to make more complex games. And we can make a lot more complex games, but we just want to make sure that they really run everywhere. What else? Yeah?
Is it a turn-based game?
It's a one-player game. So, yeah, it's turn-based.
Turn-based. So what is the time? Yeah? Or the times?
So the time is the time of the animation. So even if you have discrete changes in a board game, for instance, imagine that you have a game of chess, and then you move one piece to the other side. If you click here and then you click here, it might actually transition. So even though it's a discrete game, yeah, it's the turn-based, but you still may have animations and things like that. And the animations happen in real time. One of the things that I'm working on right now is a version. So traditionally in FRP, time was real. Conceptually, it was real positive, and operationally, it was a double. And I have a version of Yampa that is parameterized over time, so it only has to be monotonically increasing, but it doesn't have to be a double. The good thing is that you can still express FRP things for turn-based games, and then you just have to integrate timelines. You take different timelines and you just put them together. Yeah, you can have a discrete type like int, and then another discrete, more real type like double, and then you have a complete game that is double. You just have to map ints to double and doubles to int. What else? Yeah, nothing here, nothing here. So the question is, does it really prove that we can do games? I mean, after all, we're talking about game like Breakout. We're talking about a board game. And the truth is, in my opinion, is that it does. And games don't have to be so complex. You don't have to do 3D. This is Angry Birds, which spawned many different games and a TV series and merchandise that you can buy at the supermarket. And it's a 2D SDL. Well, I don't know if everything's 2D, but it's definitely an SDL2 game, at least on Android. They don't even have to be so complex. They don't have to have amazing assets. This is a very old game that someone made a remake of it. And I went to Google Play and just went to top rated and best sales and started picking games from there. And this was there on the top of the list. Tell me that we didn't see already everything we need to know to create something like this. Come on. Yeah. Please, take the center. And yeah, so this is a Haskell game that a company wrote a while back, and it's called Nikki and the Robots. Eventually, they decided not to market it anymore and to just release it as open source. This uses actual proper physics, not what I spoke about. Oh, I didn't answer your question about physics. I didn't answer your question that you could go into the future and whatnot. Yeah, so the thing about time, what was it that you asked about time? Yeah, so if you go way into the future, what happens is that you get weird. For instance, if you're doing physics, what you get is something like a ball is going through a wall or something like that. It's like you simulate further into the future, you might see situations that would never have passed and are very far away from the ideal meaning of what you described. If a ball is going that way, if I simulate every single step, then at some point it will collide. But if it just goes that way, and I simulate now and 15 years from now, then it would be way into the wall already. So you need to correct that. I'm also working, there's a branch of Yampa that includes monads. And it's not so interesting to do I.O. It's actually interesting because one of the monads that you can use is a monad with the nearest time that you should look at. So a signal function could tell you, by the way, make sure that you poll me in 0.3 seconds because something important is going to happen. And when you go through the whole signal function, the monad is defined to take the minimum of all the monadic actions. So when you go to the end, you got the closest time that you should look at. And that's just you define it separately. You define monadic Yampa plus a minimum monad, minimum time or closest time monad. And when you put them together, it behaves this way. So you know the next time that you should look at, and you make sure that you simulate at that time. Yeah, we'll be done in, yeah. Just 1 second. So essentially, these games are really, really, really simple. We have triangles, squares, and lines in this game. Okay? And this is incredibly addictive, by the way. This game is incredibly addictive. And you already know Flappy Bird, which, by the way, there's a version of Flappy Bird in the repository if you want to play it. It's in Yampa, and I think it's something like 280 lines of code. Okay. The only difference is that it uses drawings instead of pictures, but if you put the pictures, which you already know how to do, it would work in the same way. And there are pictures that you can use to implement this game also on the assets that are on the website. And that's pretty much it. That's what we do. If you have any questions now or later, well, now I don't think we have any more time for questions, but yeah, we can do it outside. Thank you very much.